So part 4 of the 6-meter AM transceiver. Some of you are getting a little bored on this thing. Hey, who uses 6 meters AM anyway? This was probably more popular a few solar cycles ago, but there are still people playing with 6 meters, mostly FM, and some single sideband for some DX work. AM is a lot of fun if you can find a group of guys that are within, say 20, 25 miles of each other. You can have a pretty good round table in a small community. Now, I don't have too much 6-meter activity around me. I will attempt to make some contacts with this. And it's probably going to turn out to be some type of a schedule that I make with someone to actually make a contact on 6 meters AM. Our last video, we had a few things to take care of. First of all, we need to get our modulation up. It's a little bit anemic on the modulation, so we'll work on a way to get a little more gain in the audio chain. We've never done a full alignment. Let's go through a full alignment on the transceiver. I need to put some kind of antenna in the air so I can make a contact. And then hopefully we'll be able to make some kind of a contact with the 6-meter transceiver. So here it is, part 4, the Lafayette HE45b transceiver from around 1962. A lot of you guys recognize this microphone. This static is a power mic. You know, it has a gain control. This is the circuit board that's inside the static power mic. It takes a 9-volt battery. It has a pretty complicated PTT switch to save power, so you only are drawing power when you PTT. This was defunct. It wasn't working. I didn't feel like troubleshooting it. It looks like it's a single transistor amplifier. So all of this just for one transistor amplification. I wanted to design a power mic, keep it fairly simple, but a power mic designed for this cartridge, high impedance like they had to do. Where I started was with the element itself, okay? And I'm just going to do this. I do have a coupling capacitor, and then I go into a resistor to ground. And then we're going to go into an FET, a JFET. And you could use almost any JFET. I used a 3819, but you can use an MPF 102. I biased it up. And then I gave it a drain load, and then set this point to half of what the VCC was going to be. So that meant I could directly couple into an emitter follower. So we'd like this to be around 4.5 volts here, or maybe 4.8 volts. You have the drop here. It's not critical because this is such low voltage. This could be anything from 3 volts to probably 8 volts, and it would still work. And then this goes right up to the 9-volt rail. And then I'm going to use the original potentiometer that's in the microphone because it's pretty and it sticks out, okay? This is larger than I'd like it to be, but it worked okay. It's a 10K. I think a 5K would be more appropriate, but that's fine. Then we come out of that capacitor, and this comes down the coily cord. Okay, that's my audio output. Up here I have a 9-volt regulator, so there's obviously some bypassing needed each side of the regulator to keep it happy. And this goes down the coily cord as well to bias it up. So that's the power mic. Rough values, this is a 10K, this is a 1.5K. I think I used a 2.2 meg. These are just 10 microfarad caps. Nothing critical there. The input, I think, is just a 0.01. 2N, 3904, and this is a 2N 3819 or an MPF 102. They have different pinouts, by the way, so be careful. And I don't have the radio on, but I do have 12 volts going up the mic to the regulator, so we should have output. So let's take a look. 1, 2, 3, 4, 5. Hello. 1, 2, 3, 4, 5. The static mic looks pretty good on the screen. We're sitting at around 4. Let's take it up. Hello. Oh boy. I'm over a foot away. Hello. 1, 2, 3, 4, 5. 5. Yeah, this is going to work fine. This is a very flexible power microphone circuit. You can basically put whatever resistance you want on the gate of the FET. So this thing would work fine with dynamic microphones as well. Just need to lower that resistor value appropriately. As far as RF goes, yeah, it is possible that you could get some RF into this microphone. So putting a ferrite bead on some of the cord lines, going down through the coily cord, not a bad idea. You can also degenerate the stage by adding capacitors here and there. This was okay. There was nothing getting back in. Now, with a real antenna, there might be a different story, but this board was a simple perf board with a copper tape ground plane on the bottom and everything grounded together as best as possible up in the microphone. Okay, we've come quite a ways with this thing. Now with the power mic, I'll let you listen to that. 1, 2, 3, 4, 5, 1, 2, 3. 1, 2, 3, 4, 5, 1, 2, 3. You can see the modulation looks glorious. Boy, that's a lot better than we had before, but having the power mic overcame most of that hum problem. There's still a little bit of residual hum. It's probably related to the case more than anything at this point. The way I'm taking power is I'm coming off the cathode of the modulator, going through a Schottky diode to a larger capacitor that provides the raw 12 volts that's going up to be turned into the 9 volts in the microphone. So that's how I'm doing that. Would it be better with a battery in the microphone? Of course it would. Just doing what I can do here. But this guy's ready to go on the air now. We're ready to get on the air with 6-meter AM. Next we do an alignment, quickie alignment, and then get it in the case, make sure everything's working, and then after that we can get on the air. We have some noise coming out of the receiver. Let me turn that down. So alignment. Alignment starts with the transmitter, and we're going to be just keying the mic, looking at the watt meter, which you can't see, but it's over here. And we'll be adjusting L1 and L6. L1 is the oscillator tripler right here, and then L6 is right here. It's a doubler. So those are the two major adjustments. And then, of course, the tank loading and tuning controls. And we're just looking for maximum out on the meter. Now be careful. This is high voltage here on the plate cap of the final. I've got a insulated plate cap on here just to show you that if you wanted to, you could actually convert that over to a much safer system. You could put heat shrink over everything, have the plate cap, and at least that gives you a chance to not get a shock. The actual tank coil down here is isolated through the coupling capacitor, which is a 2 kilovolt unit. You don't like to depend on that, but it's there. We try to avoid high voltage. First we'll do the tripler coil, then we will do the doubler coil, then we'll try to maximize things. Let's try it. Okay, I'm seeing something on the meter. First I'll show you the doubler. See how easy it is to slip off that? See, I'm not getting much out of that. That's broad tuning because it's got more than enough drive for the next stage. You do end up seeing a little bit more with the tripler. Oh yeah, see, did you see it move? But we are maximized. Now we maximize the tank. And you can adjust the loading. This is the loading control down here. That's it. That's all there is to aligning the transmitter. When you change frequencies, you may find that if you're even 500 kilohertz away from this, you won't be maximized anymore. So you might have to go back and touch up the transmitter for all of your crystals. Usually all you have to do is readjust the tank. You have plenty of drive throughout most of the band, so it should be fine. Okay, let's look at the receiver next. And with the receiver alignment, there's a front end adjustment and an IF adjustment. We're going to be doing the IF first. The IF in this receiver is 1650 kilohertz. It's the top of the AM band. That was a fairly popular IF to use for higher frequency receivers, 10-meter dedicated receivers, 6-meter dedicated receivers could use that frequency. And there was nothing on that frequency in the old days, so it was a clear frequency. Not today. There are signals in the top of the AM band that far up. So it talks about using a signal generator with a 30% 400 cycle modulation. And they want you to tap in pin 2 of V2, the mixer tube. That's how you tune the IF. I don't like that. I'm going to bring the IF right into the RF input of the SWR meter and just turn it up enough so that it blasts through the mixer into the IF. I think that's a better way of doing it. So let's get that hooked up. I have set the generator to 1650 kilohertz, and I can already hear the 400 cycles coming through the speaker. For safety, I have disconnected the microphone completely. I don't want to accidentally PTT into my signal generator. So I have my RMS voltmeter connected right across the speaker terminals. I'm going to turn up the generator a little bit more. Now again, we're blasting right through the mixer. Let's get a tuning tool. Okay. Very nice. So we've definitely peaked up the transformers. It doesn't say anything about the bottom of the transformers, but I assumed. So let's look in the bottom here. There we go. See, it always pays to go that final step of tuning the bottom of the IF transformers as well as the tops. Let's get her laid down again. We'll retouch the tops. Okay, I'm pretty satisfied that we have the IF tuned. And again, we are going straight into the radio, into the antenna terminal. We're not attaching to the mixer as they suggest. This guy is in the middle, even though the dial doesn't show the middle. It is in the middle of the capacitor range. Take a look at the S meter. That's what we're using. And then the top. I don't know what that beat note is. I think it's my counter. Okay. Oh yeah. Okay, the receiver is tuned up. So that's it. Transmitter and the receiver are both completely tuned now. So finally, we have this control right here which sets the dial calibration. So to do that, Basically, all we're going to do is go to a known frequency like 50.4 and put the dial on 50.4 and put the spot on. Actually, that's pretty close. But anyway, if you did need to adjust that, it's that control right there. So let's tune up the Lafayette HE45b. Now I'm running into a dummy load. When you're playing with the radio or just getting used to tuning it up, that's a great idea. So the first thing you want to do is make sure that the crystal works that you've inserted into the socket. So the way you do that is you select a crystal position. I'm on 1, so that's 50.4. And then you're going to want to make sure the receiver's on the same frequency. So you get two things done at once. I've got the spot function on. I know the crystal works. The S meter is showing a peak, and we know that our receiver is tuned to the same frequency as the crystal. The next thing we want to do is tune up the transmitter, so we use the microphone. We're going to key the mic in the forward power position of the meter, and we're just going to tune it for maximum. There it is. Now that should coincide with the watt meter. Now how do we know we're modulating? When we're modulating, you will see the needle just wiggle a little bit. That's a sign that you're modulating. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. You see that wiggle in the meter? 1, 2, 3, 4. That's modulation. So that's it. That's all there is to tuning up the transceiver. There is no mic gain control. So the way that I set that is with the gain control on the power microphone. Next thing we want to do is attach the antenna and turn up the volume. And we want to make sure that the front end is tuned correctly, the preselector of the receiver. There's also a noise limiter. Attached to the antenna, let's check the SWR. This is WU2D, Whiskey Uniform 2 Delta. This is forward. This is WU2D, Whiskey Uniform 2 Delta, and this is reverse power. A perfect match to the antenna. So let's talk a little bit about antenna polarization. And 6 meters is kind of brushing on VHF, so let's talk about polarization from the standpoint of 6 meter operation. We all know that cross polarization or mismatched polarization can cause 20 dB or more of signal loss, and it also promotes fading distortion with mobiles. You need the transmitting station and the receiving station to have the same polarization for the best communication. First used extensively for mobile communications, the old-fashioned omnidirectional whip gave a low-angle radiation pattern that worked great for mobile operations. Unfortunately, vertical polarization, as with mobiles, does expose the station to more man-made and atmospheric noise. Basically, this was overcome with FM, Armstrong's FM system, in mobiles. But soon, horizontal polarization became popular for the VHF AM DX community. Now with spacecraft, including satellites, these are prone to be spinning around or in the wrong orientation, so you can't really have a linear polarization like vertical or horizontal. You need to have a circular polarization. So with circular polarization, you can handle, of course, circular polarization to circular polarization gives zero loss. But if you happen to encounter vertical or horizontal polarization, it still works with only a 6 dB penalty. So circular is very popular for space communications. Now I needed to design a horizontal antenna that didn't have too much directivity to give me the best chance to actually snag a station to talk to. So I did not want to make a beam or use a beam. The logical solution was an ordinary dipole, but dipoles seemed kind of boring for VHF, so I opted for a vertical loop solution. The loop is shorted. This is good because you have less noise pickup.
It's effectively two dipoles in phase, so you get some low-angle bidirectional gain, plus you can shape the loop to give an almost perfect match to your line without a matching network. Okay, I'm in Momanagal. I'm going to open a previously made file. Okay, as you can see, this is a rectangle. It's in the vertical plane, fed at the bottom, so it's going to be horizontally polarized. We're going to see currents along here and along here. So this is really a broadside array. It's going to transmit this way and this way using these two horizontal elements. Now you might ask, well, those are short. Aren't you taking a penalty by not having a square type loop? Yeah, there's a slight penalty, but we find that most of the current in a dipole is within the 1/3 point of the size of the dipole. So this rectangle does not markedly reduce the gain. What's more important is the spacing between the elements. The greater distance between these two elements actually improves the gain of the loop. So this is not a bad shape. If we were to make this a little bit thinner, it would match 50 ohms perfectly. But right now, I'm going for 75 ohms. So let's take a look at the geometry. As you can see, this is a total of 6 meters, and it's broken up into these segments to represent the vertical rectangular loop antenna for 50.4. So let's look at the calculation, and let's run it. I'm just saying 10 meters for height in the middle of the antenna with a real ground. So let's start it. And as you can see, it's coming out at 75 ohms with almost no reactive component. Now, in a 50 ohm system, this would be a 1.5 to 1 SWR, but because we're trying to match 75 ohm coax, this is an absolutely perfect design. So this is what it looks like. As you can see, the major lobe, and this is where we measure the gain, is low angle. So this is giving us quite a bit of gain. It looks a lot like a dipole. It's a figure 8 pattern. Anyway, that's as far as I'm going with the Momanagal design, but I wanted to show you that you can absolutely design a rectangular loop that gives you maximum current radiation off the horizontal elements.
Okay, so this is the test antenna, the 6-meter loop. It's a rectangle. Now, we know that a full wave loop on 6 meters is going to be 6 meters. Hey, that's a good one. That's about 20 feet of number 12 wire. And if you have the shape in a perfect square, you get about 105 ohms of impedance. If you use a 75 ohm matching section, you can easily match that down to 50 ohms. However, if you make the shape different, like a rectangle, you can actually match it directly to the coax, and that's what I've done here. In this case, I've made the rectangle the right size to match 75 ohm coax. If it were made even more rectangular, you could do 50 ohms. Wouldn't make much difference. I'd say probably 3 inches of difference to get down to 50 ohms on 6 meters. Notice we have 4 ferrite beads. Those easily provide a beautiful choke for the loop. 4 beads will easily be as good as any balun you could build. Okay, after 100 feet of RG6, we're back in the shack now. By the way, these connectors for this thicker RG6 style coax, you can find them, but generally I take the RG59 type connectors and drill them out big enough to fit the coax. So it's not fun, but it can be done. So let's explore what we've got here with this analyzer. Looks like we're at 67 ohms. And of course, this is a 1.3 SWR because this is a 50 ohm instrument, but we're looking for the raw impedance of the line. So as we go down, the impedance goes down. Okay. Where is it? 75. Perfect. There we are. 50.672. Okay, close enough. This is just showing that we have a well-matched loop, we have well-matched coax, We're back at the rig, of course, and you're going to say, well, how do we match the rig to 75 ohms instead of 50 ohms? And the answer is, this radio has a nice pi output, and it can easily load into 75 ohms. Now, if you have a SWR bridge that happens to have a 75 ohm setting, you can use that too, but generally just a 50 ohm coax from the analyzer back to the rig is good enough, and it just tells you that the antenna is not broken. Yes, you can find SWR bridges that are set up for 75 ohms. Okay, so these exist, guys. And it's a Lafayette. WA1YKL, I'm starting to pick you up now. You must be getting a little around Wellington Hill. WA1YKL from WU2D. Okay, WA1YKL, this is WU2D. You're starting to come up now.
Just coming by Hanover Street exit.
Yeah, just as soon as you got up on 93, you were around Wellington Hill, and I could pick you up. You're about S9 now.
Yeah, you have pretty high noise level, but yeah, you're up to a good solid 5.
Yeah, you're starting to come out of the noise now. You were around a 5 or 6 and flipping all over the place, but starting to come up. The problem is we're cross-polarized, and that makes the signal really wonky.
Just getting on 101 here.
Yep, you're a solid S9 now, and starting to come in pretty cleanly.
Yeah, WA1YKL. What's your call sign these days, Mike?
Whiskey Uniform 2 Delta.
U2D. There you go, I think.
Yeah, you got it. WU2D. So you're just around exit 1 on 101, over?
Yeah, just coming by the New Hampshire DOT. They're coming up on exit 1.
So this thing was a lot of fun to play with and bring back. You know, it's representative of equipment from the early 60s. You're going to have CBs, stereo equipment, and a lot of these 6 and 2 meter rigs of this class that you're going to see at the Hamfest. Usually they're going to be available for between 10 and 50 bucks, and it gives you a really fun winter project to bring one of these back to full performance. And it's a lot of fun to use on the air as well. Get yourself some 8.4, 8.5 megahertz crystals, and let's see you on 6 meter AM.